All right, hello. We just finished up chapter 2 and we're getting ready to start chapter 3. So more recently, we looked at, we explored the idea of graphical summaries, right? And we said that the type of graphical summary that you do depends upon the type of variable that you're working with. We said for qualitative or categorical variables, the two most widely used types of graphical summaries are the bar graph and the pie chart. Talked about the pros and cons of each of those. We said for quantitative, for numeric variables, we looked at a few different things. We looked at a frequency table, both raw frequency and relative frequency. We also looked at a histogram. We spent most of the time talking about the histogram. And then we very briefly talked about a stem and leaf plot. Now, along the way, we hopefully gained an appreciation for the power that these graphical summaries offer us, right? They're very good at quickly impacting upon us the message or the information, the story that variable might be telling us. That's pretty cool. For example, as archaeologists, we came to the conclusion, based off looking at our histogram, we probably don't need to dig any deeper than whatever it was, 100, 120 centimeters. As foodies, right, we looked at a stem and leaf plot. We said, you know what, I probably am not going to eat here. I'll find my bread and butter somewhere else. That said, we also talked about some weaknesses, right? We said if somebody asked us to talk about like what's the average depth of an artifact, what's the average rating for this particular restaurant, how much variation is there amongst the depths, how much dispersion is there amongst the restaurant ratings, that this is an answer that's difficult to answer just based off the graph. That is, we all come up with some sort of answer, but we probably come up with slightly different answers, and in some ways that's not satisfying. We would like to have a more concrete, a more black and white, a more objective way of measuring important characteristics such as the average, important characteristics such as the variation. And to do that in a concrete way, we need to do that numerically, and that's going to be the goal of chapter 3. Chapter 3 is going to kind of tell us how to do all this stuff. It's going to address all the weaknesses that we observed last chapter, starting with this idea of measurements or measures of center, which again is just kind of a fancy, weird way of talking about measurements of average.
So averages are a part of our everyday vocabulary, right? It's one of those phrases or terms that we use all the time without even thinking about it, right? Your GPA, obsess may be a strong word, but your GPA is a grade point average, and hopefully it certainly is something that we care about, right? We do a lot of work to do well on tests. Why do we want to do well on tests? Because we want to get a good grade in the class. A good grade in the class will boost or keep our GPA high. Right? Averages, or at least this concept of average, are often used without us even really knowing it or thinking about it. Right? Doctors or whoever, articles on Yahoo, tell us that we need 8 hours of sleep a night. Now, are they really expecting us? Are they really expecting us to get into bed, set our alarm clock, instantaneously fall asleep? Alarm clock goes off exactly 8 hours later and we hop out of bed? Of course not. Right? When these doctors are telling us that we should get 8 hours of sleep, they're understanding that sometimes we're going to get more, sometimes we're going to get less. What they're sort of urging us to do is sort of on average get 8 hours of sleep. Right? When you buy a new car and it says whatever that you're going to get 35 gallons or 35 miles for every gallon of gas, are they really saying that if you were to measure it, that every gallon of gas is going to get you exactly 35 miles? Of course not, right? They're saying, depending on road conditions, depending on how fast or how slow you're driving, depending on traffic, you might get a little bit less than 35 miles to your gallon. You might get a little bit more. What they're saying is on average you're going to get 35 miles to the gallon. Now, our book talks about two main types of average, two ways of measuring the center. the median, and the mean. Now, you've probably been exposed to a third one, that is the mode. We'll talk briefly about that, even though it's not in our textbook. I think it gives a more complete picture of what's going on. Let's start with the median. The median is the central value of an ordered distribution. That word ordered is extremely important. It can also be thought of as the 50th percentile, right? 50th percentile, say you're talking about a test. The 50th percentile of the median, it's the number or the value such that 50%, half of the class did worse than it, and 50%, half of the class did better than it, right? Just like the median of the road, right? The median of the road splits the road in half. The median of a data set or the median of a variable splits the actual variable in half. Splits the numbers in half, the scores in half. How do we find the median? Well, the first step is we need to order the data from smallest to largest. Then what we do, it depends on whether it's an odd sample size or an even sample size. If it's an odd sample size, then there will be exactly one number in the middle. That number will be the median. If it's an even sample size, then it turns out there'll be two numbers in the middle. And it turns out then that the median is going to be the number exactly between these two numbers. A lot of times we can maybe figure that out just from number sense, but it turns out we don't have to. We can always use what's called the midpoint formula that says if you want to know the number that's exactly between two numbers, you add those two numbers up and divide by 2. We'll see an example of this soon enough. So let's consider test scores from a Math 121 exam. And so here are the test scores, 100, 98, 97, right, all the way to 70. Let's see, how many are there? I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 13 test scores. Now let's go ahead and let's find the median for these exam scores. So first step is to order the numbers. They actually were ordered, if you look on the previous slide, from the largest to smallest. And actually that will work. But just for consistency, I'm always going to order from smallest to largest. So I reorder them. I put them in order from smallest to largest. Now, remember I said there was 13, so that's an odd number. Since it's an odd number, there will be exactly one middlemost number. I need to figure out what that is, and that'll be my median. So I start at the most extreme numbers. The most extreme numbers are 70, it's the smallest number, and 100, that's the largest number. I then move inwards, right? The second smallest number is 83. Second largest number is 98. I move in again. The third smallest number is 83. The third largest number is 97. I move in again, gives me 86 and 94. I move in again, gives me 89 and 90. Move in again, gives me 89 and 90. And then I move in one more time, there I am. Boom, bingo, the middlemost number. That's the median. So in this example, in this case, the median ends up being 90. Oh dear. Oh dear, how sad. I always hate seeing this as a professor. It turns out after running a pretty sophisticated statistical algorithm and running those tests that we just talked about through the algorithm, it turns out that the student, the student who scored 100 points, it turns out that they got caught cheating. And so what sort of happens to cheaters? They just sort of go away. They just sort of vanish. I'm not really sure, to be honest, where they go. Maybe they go to Siberia. Maybe they go to Narnia. Maybe they go to Westeros. I don't know, but they're just sort of gone. And of course, if they're gone, then their score of 100 is gone. So now we have 12 observations, not 13, and now we need to recompute the median. So let's go ahead and do that. So here we are. This is an even number of observations. Same basic idea. I start at the extreme number, so now the largest number is 98, smallest number is still 70, and I kind of move inwards, right? So I move in from there to 83 and 97, 83 and 94, 86 and 90, 89 and 90, boom, I'm at the middle. So in this case, there's two middlemost numbers, 89 and 90. The median is the number that falls exactly between them. Now, I think most of us can look at that and say, oh, okay, the number exactly between 89 and 90 is 89.5. You're right. But if for some reason we couldn't see that, right, or if this was an example where it was more complicated, say we wanted to know the number between 37 and 74, we can always do this by adding the numbers up and dividing by 2. So go ahead and try it in your calculator. 89 plus 90, divide that by 2, and you get, in fact, what we knew the median was. You get 89.5. Alright, so that's the median. The mean is the most commonly used measurement of average, and as we'll talk about at the end of the slide, it's something that's sometimes sort of used a little too much, and hence used in situations where it's inappropriate. The mean is how GPAs are calculated. It's, I think, how most professors calculate things like test averages. Certainly how I do my test averages. The mean is determined, it's calculated, it's computed by adding up all the numbers in the sample. So adding up all the numbers and then dividing by n, the size of our sample. We can sort of write this little algorithm, we can write this approach up using a special summation symbol that I'll show on the next slide. So we can write the mean as, well, a few things. So first, we often abbreviate the sample mean. Rather than write the word or the phrase sample mean over and over and over and over, we often abbreviate it. We abbreviate it with X bar, right? It's the letter X with a little bar over it, a little horizontal bar. We verbalize that as X bar. That's our abbreviation for the sample mean. We're going to use it a lot in this class. We'll use it fairly regularly throughout Chapter 2. It'll kind of go away for Chapters 3 and 4, but it will come back with a vengeance in Chapters 5 or 6. So we might as well take the time now to try to internalize in our brain, right, memorize that abbreviation. X bar equals sample mean. So what is the sample mean? Well, the sample mean is this summation symbol. That's the capital Greek letter sigma. Looks like a large letter M that someone sort of cow-tipped onto its side. So the capital letter sigma, that's just the add 'em all up symbol in mathematics. That X just is like a placeholder. It says like an observation or a number. And remember that N is a very common abbreviation for sample size. So that's just a very terse, very compact, symbolic way of saying, right, the process or the algorithm that gives us a sample mean, that says that we find the sample mean, we find X bar by adding up all the values, right, summing over the x's, that's what the numerator is saying, and dividing by n, dividing by the size of our sample. Now, I don't care so much about whether or not you recognize that summation symbol. I'm mostly exposing you to it, because if you're reading along in the textbook, which I hope that you are, you will encounter that summation symbol in the textbook, and it also will come up when we talk, I guess it'll be the next PowerPoint when we talk about sample standard deviation and sample variance. So, let's go ahead and calculate the mean for our previous 121 exam. Now, right, all I'm doing is, if you go back, these are all the scores minus the cheater who got 100. So the 12 remaining students, I take all their scores, I add them up. It's tedious. It's very tedious. Even having a calculator do it for me. I add up the 12 numbers, I divide by 12, and I get 88.25. That's the mean. Out of curiosity, how many of you at this point know what the mode is? Ah, good, good, good. I'm very impressed. The mode, remember, is the number or value that occurs most frequently. So, right, looking at these numbers, right, the ones I'm adding up are essentially my observations. The number 90 occurs 3 times. It occurs more often than any other number. So we would say that the mode is 90. All right. So in this example, we know that the median was 89.5, the mean is 88.25, and the mode is 90. Right. All very close to one another. Well, all very close to one another, but yet at the same time different as well, aren't they? And so, I mean, at this point, I probably have not taught you anything particularly new. That is, probably the vast majority of you came into this class knowing how to compute a mean, a median, and a mode, right? You may or may not have been rusty regarding it, and I may or may not have helped kind of remind you, right, how to do it. But what maybe is hopefully new for you, and perhaps something that we could do or finish things up with that will expand your horizons, is to talk about sort of the pros and cons, right? The strengths and weaknesses of these different averages. Because if there's three different ways of measuring averages, it sort of begs the question, right? Well, which way should I do it for which situation? It's a really good question. So let's start with this. You in practice almost never use the mode. The mode, that's why the textbook doesn't even bother teaching it. There's a lot of potential problems with the mode, right? A lot of times a mode might not even exist. That is, if you have a set of numbers where nothing occurs more than once, well, then everything's occurring the same amount, and there is no mode. You sometimes can have 2 or 3 modes, which happens fairly regularly. That is, right, there might be 2 different numbers that occur 3 times each. They might be drastically different from one another, and then it's unclear what the mode is. And I could come up with a whole other slew of examples where the mode is just sort of a deceptive, distorted, inappropriate way of measuring an average. Now, the one thing that a mode does have going for it, the one feather it has in its cap that the mean and the median cannot compete with, is that the mode can be used for categorical. Categorical just means qualitative. Can be used for qualitative variables, right? If you're looking at, say, the colors of M&Ms, you can look at something like the mode color. The mode color would just be the color that occurs most frequently. So maybe something like blue. Maybe that's the M&M color that occurred the most. You cannot do a mean color. You cannot do a median color. Right? The mean requires adding up all these observations. We can't add up categories. We can't add up colors. The median requires this ordering process, right? And it's a numerical ordering. You might say, well, you could like alphabetically order the colors, and that's true, but that's a somewhat arbitrary ordering, isn't it? Because if I did it in Spanish, then I would order the colors differently, and I would get a different median. If I did it in French, I would order the colors differently again and get a different median, right? That is, I want to, regardless of what country I'm doing this in, to get the same numerical answer, and I could only do that if I'm working with values that have a numerical ordering to them. So generally, if it's quantitative, we use means or medians. If it's qualitative, we can use a mode. So let's restrict our attention now to quantitative variables. If it's quantitative, should I use a mean or should I use a median? It's a really good question. Part of what the answer boils down to, actually the main thing that the answer boils down to, is the fact that the mean is not what we call a resistant measurement. A resistant measurement is something that is not unduly influenced by extremely high or extremely low numbers. The median is a resistant measurement, so that gives it a bit of a leg up on the mean. Now, before we talk about the implications of this, let's look at an example to get kind of a better understanding of what I mean by resistant measurement. Let's say that we're hired. We're hired by the University of North Carolina, UNC, to write a really cool, colorful pamphlet advertising their cultural geography program. And of course, right, we're gonna advertise all kinds of things in this pamphlet, probably primarily just how much fun cultural geography is. and what a rewarding career it will be. But at the same time, right, I know everyone is, I don't know, has their own varying levels of how much of a mercenary they are, but at the end of the day, we all have to pay our rent, and so how much money we're going to make at our job does matter to some extent to all of us. And so we would want to advertise in our pamphlet how much a student can expect to make with a degree in the exciting field of cultural geography. And so, right, to be able to determine this, what would we have to do? We would have to take a sample of alumni, a sample of students who have graduated from our program and went on and gotten their jobs and started their career, and we could ask them how much they're making. So, I mean, we would do much more than 5 alumni if we were to do this. We would take a much larger sample, but just working with 5 will make this example a little bit more accessible, and I assure you that the overall point would still hold if we did 30, 40, 50, 60 alumni. So let's say that we take a sample, and so we call the first alumni and we say, hey, how much are you making in terms of cultural geography? And they say, oh, I'm making $40,000. We say, oh, that's great, good for you. We call the next person, they're making $50,000, even better, we're so excited for them. We call the next person, well, they're only making $30,000, but it turns out they just graduated, they're getting started. We give them some words of encouragement. We move on to the fourth cultural geographer, and it turns out, whoa, what the cutta? Holy smokes, they're making $20 million a year. Well, we definitely congratulate them. We shake our head with disbelief. We call the next person. Right. Unfortunately for that next person, right, they make $60,000, and if we hadn't sampled that fourth person, we'd probably be impressed by the $60,000. But, right, I don't know about you, I have a little bit of a shell shock now, and $60,000 seems a little paltry compared to Mr. or Mrs. 20 million. Now, I leave it to you to verify these numbers. So I put the median there, I put the mean there. The median salary, the mean salary. Now notice, I don't know, it may or may not be tempting for you to say that the median is 30,000. It is not, right? The first step that I have to do to compute the median is I have to order those numbers first, and they are currently not ordered. If I were to order them, I would have 30,000, 40,000, 50,000, right? 50,000 would be in the middle. Then 60,000, 20 million. So the middlemost number, once they're ordered, is the median salary. That's $50,000. The mean salary is we add those 5 numbers up and divide by 5. I leave it to you to verify. That ends up being $4,036,000. Holy smokes. Yeah. It's perhaps a little late for me to change my major, but it's maybe not too late for you to change yours. Maybe you, yourself, want to consider the exciting field of cultural geography. What happened? Where would you go wrong? Because probably, hopefully you agree with me that that 4 million sounds awfully nice, but it's not a realistic number looking at what's going on in our data set, right? Probably we would say that most of the people are making somewhere in that $30, $40, $50, $60,000 range, right? In which case the median of 50,000 is a very reasonable number for the average. And there's this one person, just this one flukish person, who's making 20 million. Now notice, this one fluke, it doesn't seem fair that one person, one number, could carry so much weight. It's not democratic. But we see that that is in fact what happens with the mean. That one person, who by the way is Michael Jordan, yeah, Michael Jordan, UNC alumni, who got his major in cultural geography, and we just happened, I assure you, he was randomly selected, and right, he was having a bad year, which is why he only made $20 million, right? By accidentally sampling Michael Jordan, right, his salary, we can see quite clearly, distorts the mean. It pulls it way up. That's what we mean by saying that the mean is not resistant, right? It's not resistant to the influence of Michael Jordan's salary. Whereas notice the median is resistant, right? In fact, Michael Jordan could be making 20 kajillion, kabillion, umpteen illion dollars, and that's going to make the mean blow up to be outrageously large. but the median is still just going to be $50,000. Agreed? So hopefully we see what I mean when I say the median is resistant. A handful of small, well, in this case, a handful of large, but you could have the same problem on the other end of the spectrum, a handful of small numbers. Neither one of these unduly influences the median. Although, as we can see quite clearly, they do influence the mean. So what's the conclusion? Where am I going with this? Well, at a glance, and based on what we've talked about on this PowerPoint, you would actually maybe think that the median is a superior measurement of average. Really in almost every way. It's kind of grammar-friendly. By grammar-friendly, I just mean it has a nice intuitive definition for what it is, right? The median is that 50th percentile. It's the value that splits your data set in half, right? If it's the median test score, half the class scored less, half the class scored more. That's a very intuitive way of describing the average. The mean, even though we've been brainwashed from a small age to just sort of accept it for what it is, it's not particularly intuitive. Add up all the numbers and divide by n. It's not obvious, if you really think about it, that that's a good way of measuring the average. The median is resistant, whereas the mean is not. So, based on this information, we would think that the median is the better way of measuring average, and so it might be a little surprising, right, that we live in a mean-dominated world. We might be left wondering, why is it that everyone uses the mean? Well, it turns out that the mean does have one incredibly magical, unbelievably miraculous property that makes it such an incredible way of measuring an average. And we will learn what this magical property is. Yeah, pretty exciting. But this is the sad part. We need to wait until not just Chapter 4, but the end of Chapter 4 to learn what that property is. The mean does have one thing, one heck of a feather in its cap, that places it above and beyond the median, that puts it in a situation where we always want to use the mean whenever possible. However, as we saw with the Michael Jordan example, in situations where you have a handful of really big or really small numbers, you cannot get away with using the mean even though you would like to. Now, it turns out that this idea of just like one or two really big or really small numbers can be sort of detected by looking at the histogram. Remember, histogram's what we talked about in the last PowerPoint. And it turns out that idea of skewness that we saw in histograms, that is indicating, right, a handful of really big or a handful of really small numbers. Now, it's not written, I think, on this PowerPoint, so pay attention to this, right? If there's just a handful of really big numbers, that's going to be shown as a right-skewed histogram or a right-skewed distribution. In this situation, as we saw with the Michael Jordan, the mean is pulled up. The mean is unrealistically large, much larger than it should be, and hence it ends up being larger than the median. A left-skewed distribution means that you have a handful of small values. In this case, the mean is pulled towards the small values and ends up being smaller than the median. So, right, when we say that you cannot use the mean in situations whereas one or two really big or one or two really small numbers because, right, it's not resistant, it's pulled towards those numbers, it's the same thing as saying that the mean cannot or should not be used when you have a skewed distribution. Now think back. In the last PowerPoint, we talked about situations that had skewed distributions. We said, for example, salaries, right? That's the Michael Jordan example we just did. Salaries tend to have a right-skewed distribution when you make their histogram. Which means what? It means that the mean is not appropriate to use when you're trying to report an average salary. And in fact, one of the few situations in life where the mean is not used is if you go on to say any web page that's reporting on average how much money you can expect to make in your chosen profession. If you go to the Bureau of Labor Statistics webpage done by our government and you look at, right, say how much do nurses make on average, you will see that the average salary is reported not as a mean, it's reported as a median. Why? Well, it's because, one, it's a universally accepted fact that salaries tend to follow a right-skewed distribution. It's also a universally accepted fact that you should never use the mean in those types of situations. Last PowerPoint, we talked about the idea that if you did a histogram of housing prices or housing values in a particular community, that they're going to follow a right-skewed distribution. Now, or if you're getting ready to buy a home and you're thinking about or wondering, can you afford to move into a particular community, you might look at the average housing value or the average housing prices in that community. You will notice, if you do this, that the average housing price is reported as a median price. Why? Well, because, again, it's a universally accepted fact that, like we talked about last PowerPoint, if you do a histogram of housing prices, it will follow a right-skewed distribution. The mean is inappropriate in these situations. Right? So to summarize, we use the mean whenever we can. It's got a magical property we'll talk about later. However, one of the situations we can't use it is where we have a skewed distribution. When we have a skewed distribution, because the mean is not resistant, we have to instead use the median, which is.